Brian, Nathaniel, you're both here.
Where I
Okay.
raised my hand, came on stage. I'm sorry.
Just y
I don't think I know how to not do it.
so, that reminds me, I thought of you this weekend
Yes.
when I saw that
Uh-oh.
Sam Altman was saying that being polite to ChatGPT was costing him millions.
I love that. That made me feel so great.
Yeah,
Did that? I Because it's like because I am always polite to ChatGPT, as we've discussed in the past. Like I'm just always polite to ChatGPT, and I have always felt like a little disgusted by it because I'm anthropomorphizing it, even when I shouldn't be. And then I'm also, it's like I'm a little disgusted by the whole Altman
yeah.
zeitgeist. So the fact that is costing him just, I just want it to be billions of dollars, and I just that is so delightful. It'd be interesting to know how. Certainly, I am being much more polite to ChatGPT today than yesterday.
Yeah.
I am just going way out of my way to just really praise it. I want to expand on I want to be very concrete with my feedback.
Well, I did see something by
Right.
Microsoft that said that, the more polite you are, the more likely you're going to get politeness and respect in return. So, I mean, it does seem like in addition to costing Sam Altman money, there may be some additional reward to that politeness.
I think it's great. There is, I mean, there's karmic reward and there is monetary punishment for Sam Altman. What more can you want? I mean, what a
Exactly.
twofer. Like, you don't even have to like. Wait a minute, are you being polite just because you hate Sam Altman? It's like, look, that's unknowable. Like, you can't know that. You can't know that. I'm being polite. Like, why
My
I'm
reasons
polite?
are my own. Yes.
My reasons are my own. My reasons are my own. Am I being polite out of malice? Maybe I am. Maybe I am.
Does that
Is,
undermine the politeness?
is it
Arguably.
make me less polite? Arguably a little.
Yeah.
Arguably a little. I thought that really was great. God, it warmed my heart to hear that. He should have. He really should not have said that. Not to me anyway. Not to me. I was the wrong person to hear that. So,
That's right.
all right. Well, this is very exciting. Because you would wonder after last week's absolute banger of a conversation, Adam. That was really amazing.
So wonderful.
Kate Hogger, Ryan Mack. I mean,
Especially in the
I mean,
recording. None of the audio shenanigans in the recording.
that was heroic work. That was really terrific work. But you would think that like this is the only thing that can beat this is Morris Chang. And while it would be true that Morris Chang would be it, there's one other episode that I feel can rival it, and that is of course a bring up episode. I love our bring up episodes.
They're
And
great.
did you go back to listen to any of our bring up episodes?
Yeah, I did. I did, one of our first ones, I think, the first Tales from the Bring Up Lab.
Tales from Bring Up Lab, yeah. And Nathaniel, have you gone back and re-listened to any of that, or has your therapist explicitly instructed you not to?
I have not. I lived it, and I'm
Yeah.
okay with not reliving it.
Yeah. There were some things I had forgotten. There are some details I'd forgotten there. And the thing to know about that, so when we did this episode, when we first brought up Gimlet, which was our AMD Milan-based sled, really, really painful, long bring up. And when we recorded that episode, we still had like lots in front of us that we had not, because at the end, we had not brought up T6 when we recorded that first episode. We had not, so we were still at, Adam, you recall the 499 ohm resistor that was the difference between life and death.
Yes.
That was in our future then, right? We had, we said the whole hot plug network was in our, so we were just, there was, and Nathaniel, I was going to, maybe this is a good way to kick us off, because after the initial bring up of our Rev A sled, which ultimately we were able to actually do all the necessary validation on, it just took a really long time. Nathaniel, your line to me that I'm sure you remember was, just so you know, we got lucky and we're never doing it this way again.
Yeah.
And because we had, I mean, that board had a complicated history, and we kind of, it was just, we knew we had a lot to learn from Gimlet. We also now had a team in place, and we had a lot of kind of foundation. So what were some of the big changes coming out of Gimlet as we began to look to an AMD Turin-based, we skipped Genoa for reasons we talked about when we talked about Turin, but as we were beginning to look to a next-gen compute sled, what were some of the big things in your mind of like, okay, these are some of the big things we need to change?
Well, I mean, I think a lot of it was process. So, I mean, the history of Gimlet, of course, we had some external partners helping us with some of that, and then took it over at a certain point. And so there was kind of just a sorted history of many people working on that design, and it kind of evolving both as the company figured out what we want, and also as we figured out who was going to design it. So I mean, I joined in May, and so we were, I mean, I think it depends on who you ask, but we were 3 months away from tape out in May
Crazy.
or something like that.
Yeah.
And I mean, it turned out to not be quite 3 months away from tape out, but um so I think some of it was just we didn't have like a single set of owners for that. We had like, I mean, that had started with no electrical engineers at Oxide, and then we had gotten a few, and then we got a
We
few
call, we call
more.
that the dark period. We prefer not to
Right.
speak of that.
So I mean, some of it I think and we our CAD was mostly outsourced. I mean, we were using contractors for that, and like they did fine, but it was it's a lot of like, you don't own a library, you have kind of all of this like core functionality, like your footprints and your everything is just outsourced, and you're not necessarily nobody cares about your stuff like you do, and
Amen.
so um you just don't necessarily get the quality or the understanding or the things that you're looking for. And sometimes you don't, I think, even you don't know what you care about until you have lived through it. And
Yeah.
so
Yeah.
and like, so I mean, it's not necessarily to fault any of our contract partners at all. It's just that as we figured out what we wanted to do and we figured out where we needed to play, it was something that we needed to own. And so we had footprints, and like, I mean, when you look back at the our cadence footprints, we had the same parts on many boards, but in some cases different footprints, and not like crazy different, but just they're not the same, right? And so we didn't have a consolidated part library. We were growing all of our like corporate processes and our electrical engineering design processes and everything all at the same time. And so as going into a Turin based design where we're going to have the same 6 people basically own the hardware design from the beginning, we really wanted to spend time fixing our library. We also did a CAD change, kind of in like, I guess as a precursor to this design. So we were moving to a different CAD package, and as
Well,
part of moving to good.
well, and I was just going to say that. So part of what, so first of all, people in the chat are wondering, like, wait a minute, in this kind of era before you had double E's, you had a bunch of software engineers that were actually like doing layout. Like, no, we weren't doing that. Please, we're not quite
Oh,
that
we had
bad.
we had
We,
yeah, we had electrical engineering partners, right?
but exactly, we were trying to do it as kind of an as any. It's really tough as a startup where you're trying to do so much, and we thought like, well, maybe we can engage the engineering services for this. And again, it's not like, no matter how good the kind of the partner you have is that does that, Nathaniel, just to underscore the point you made, that nobody cares about your design the way you do. And there's just naturally there are going to be different decisions that are made. And one of the decisions that was made that was like a very important decision, but was not something that and just because it was so early and it was not made necessarily exactly by us, was in EDA software, right? So we're using OrCAD and it's like there were a bunch of reasons. Like we were using OrCAD because the AMD reference design used OrCAD. That's the reason we were using it. And
Right.
like that is not a great reason to be using a CAD package, and especially for a company that wants to take a real clean sheet of paper and do things from first principles. So one of the things coming out of it was that we wanted to really make a holistic change there. We were definitely we decided that we were no longer going to be a Cadence customer. Just bluntly, we were going to be, and we were. I felt Altium was going to be just much more consistent with what we wanted to go do. So we were making a big shift away from Cadence and OrCAD to Altium in particular. That was a huge change, and we were using that as an opportunity. Like, okay, we can now like actually let's take advantage of this big change that we need to do anyway, and let's do a bunch of these things you're talking about, like having a
Right.
real library, getting footprints and so on.
Yeah, and I mean, we, at the beginning, I mean, the first tape out of Gimlet, we didn't even have Gimlet in our PLM system. Like, we were still bringing our PLM system online, and so, I mean, it's just like a lot of things had moved since that point. So we had a lot of process stuff. I would say, on the technical side, we kind of shied away from a lot of programmable logic. mostly because we didn't have programmable logic experts enough to staff any of that work. And I mean, like, programmable logic is, it can be tricky, and it has, various black box concerns and that kind of thing as well. So when I joined, I think right around when I joined, we decided to add an FPGA to Gimlet for the sequencing, which I think was a great idea. I mean, we've used that a lot, and that was good. But even
We
that was
needed that.
pretty. Yeah, it was pretty minimal in terms of its functions, and kind of like a lot of the design bones were already in place when we added that. And so it was going to be that, or it was going to be some kind of like off the shelf power sequencer that was going to try to meet our needs. But we wanted the flexibility of an FPGA, especially because we didn't know how complicated it would be to bring up the AMD chip and to sequence its power.
Nathaniel, I got a couple of things. PLM, I'm sure not everyone knows what that is. And sequencing, you alluded that it has to the fact that it has something to do with power, but I think that it'd be worth spending a couple seconds on that.
First of all, people who don't know about PLM should enjoy their innocence. Why should we force feed them the fruit from the tree of knowledge of good and evil?
Well, just let's tell them enough to know to stay away from it, to just make smart choices.
They're gonna realize they're nude. I don't know. Okay, just be very careful. I don't know. Just don't say you weren't warned. Go ahead, eat the apple. Yes, fine.
Yeah,
PLM.
PLM is product lifecycle management, and in general, it's like a big database that holds your BOM, and it often holds your whole product BOM, and it goes up and down, your product tree, and you do your changes and that kind of stuff in there. So I mean, when we taped out Gimlet A, we dumped a BOM out of Cadence into like Excel or Google Sheets, and that was our BOM for the first round of Gimlet. And we were still working on getting our PLM system up to a standard to which we were willing to use it, and we hadn't even figured out how to link up OrCAD and our PLM system. So we did eventually do all of that, but like that just kind of gives you an idea of like where we were in the we were flying the airplane and building the airplane kind of at the same time on a lot of these things. So that was that. And then sequencing. So there are a bunch of signals that go between your power supplies and your various chips. And in general, I would say the more complicated the chip, the more complicated its sequencing requirements are. A lot of these chips have multiple rails. A lot of the rails are controlled in various ways for both power and performance reasons. And if you sequence them wrong, in some cases, you're at risk of blowing the chip up. But you think about an SP3 or an SP5 socket, these big processors, so a Milan or a Turin, they want to have power domains that they can boost so that they can use more power at certain points in time. They'll even raise their voltages under control. But obviously those rails that they want to control have to be different rails than some of the other core functions, like your clock still has to run and that kind of thing. So those have a different set of rails. And so there's a whole sequence that's defined by a given chip that tells you this is the order in which you apply the rails. And then sometimes there are additional handshake signals. So we release a reset, and then they have some signal that comes back to us and toggles high or low, however the case, to let us know they've moved past that state. And so we ended up on Gimlet putting all of that stuff into an FPGA, and I think that was a good decision. I think
definitely a good decision. Yeah, no question. Yeah,
allowed us a lot of visibility and flexibility, and I mean, we control the resets to RT6 and some other stuff in there.
Well, we also, we did things like, that we put the FPGA bit stream is actually in the actual Hubris image that we load on the SP, so we're able to attest the FPGA image is attested with that SP image. There's a bunch of things that we were able to. I think it was very good to kind of get that experience with soft logic and the things that soft logic could do for us.
Right. Yeah. And so as we looked at and we went through the Turin stuff, there were a number of features and things where we potentially wanted to, open the scope up a little bit on our programmable logic side. A couple of really easy ones are like on Gimlet, we hook the SPD stuff from the SP3, so from the Milan socket, right up to our service processor. And
SPD is the serial presence detect on the DIMMs.
Yes, it's a little EEPROM.
Running glossary.
Little EEPROMs on all the DIMMs. And so normally in a normal computer, like your computer sitting on your desk, the processor is connected to it has a little I2C bus, and it connects to all of the DIMMs, and it can read out information from the memory, their serial numbers, and some timing parameters and that kind of thing. We wanted to interpose on that in our designs, and we still do. And so in Gimlet, what we did is we just wired that bus up to the SP, and the SP acts as a I2C target. And then the SP can go prefetch all of this data from all the EEPROMs and just parrot it back to them. Well, we want to keep the same SP on our Cosmo because we like our SP, and it's fine, but it doesn't have an I3C peripheral, and the industry is moving to I3C. So that was a spot where we're like, well, even if the AMD Turins right now aren't booting I3C, we want the capability of doing that. And so we either have to change our SP, or we have to build some other kind of subsystem that could potentially talk I3C. So we put that to an FPGA. That's one place. The Turins support eSPI boot. So this is a slightly, like, instead of just booting off of a dumb Spinor device, like your CMOS device for their initial instructions for their PSP and the ASP loads, those are the PSP is the hidden core in one of the hidden cores in the big CPU, and it kind of loads the initial brains. Instead of doing that, you can talk eSPI, and so you can talk to a slightly smarter device where you have some kind of multiplex channels, and you can do a number of things. And so we wanted to be able to do that.
Yeah, we did. Very promising.
Yes, yeah, we actually really love that. And one of the reasons that we drove that way was because in the turret we use two UARTs in our system, one for the console, so that's your UART 0, and one for what we call IPCC, which is our like a little control protocol that runs between the SP and the big processor. The Turin devices all got rid of their hardware handshake signals on their second UART because I think they ran out of pins, and these chips are monsters. And so in order to have a performant, we run that at 3 megabaud. In order to have a performant IPCC channel, we needed to do something else there where we would be able to do flow control. And so we made the decision to do that over eSPI as well. So that our IPCC channel is being done over eSPI, and that goes to the FPGA, which then busts it out to a UART and ships it over to the SP. So there were kind of a lot of things like that. I think we also wanted the whole hot plug subsystem in a server. So it's an I2C interface, and you're interfacing to a specific number of, it's a PCIe 9506, so that's an IO expander basically that you can buy from NXP or TI, and they're very dumb devices.
Kind of expensive little goobers.
They're kind of expensive, yeah. They're old and venerable, right? And and so and the PSP code or something in one of the hidden cores talks to these things. So you're sort of limited in some senses as to what parts you can choose, right? There are a number of supported parts, and you can kind of build out a topology that you like, and you pass that into your host software bits, and then the host software bits will interact with these devices. And so one of the challenges we had on Gimlet was we didn't have a whole lot of visibility to that stuff.
You weren't going to say the challenge that we got it all wrong, that we got the pin numbering wrong on all those. And
there was a lot of
that was one of the horrors that I had forgotten anyway, Nathaniel, was that whole adventure with Rick having to debug him, and the peril of discrete logic is like if you get something wrong, and it's just like really easy to, I'm not casting aspersions on, you make mistakes, that happens, but when you make mistakes with discrete logic in hardware, it's like, now you're actually stuck reworking this thing if you can.
Yeah, in fact, this is probably something we didn't talk about in one of the bring up channels, but on Gimlet, as we went to our production rev, we discovered that unplugging disks would not necessarily generate hot plug events.
Right.
And so we actually had to give up we support AIC NICs, which is just like a 1 gigabit add-in card. For when you have the Gimlet out of a chassis, you can stick an AIC NIC into one of our SEM slots instead of a shark fin, and we can boot in certain development modes. And so we support that. We supported that. Now the K.2 made a lot of that use kind of go away, and we don't typically do that anymore. We just use K.2s, which are basically the same thing but on the U.2 interface. But one of the things that are fixed, because it was all discrete logic, it was all chipped down, we had to change an OR gate to an AND gate or something like that. And that basically breaks the AIC use case. So you can't use an AIC on a production Gimlet without a shark fin and other things. So,
and if you can't use an AIC, then that hot plug doesn't work properly. So it's like
right.
Yeah,
so
yeah.
right. So we made the decision to make hot plug work right. But that's like, it gets complicated with all of these gates, and you have you've got a bunch of active low logic, and you have like AMD's name of things and then our intended name of things, and like decoding all of that. I mean, I spent most of this last weekend, or most of a day this last week, dealing with trying to re-decode all of that for Cosmo, even because it's complicated. But we have an FPGA, so eventually I can just write the thing that we want. So we wanted to move that into an FPGA. That was the long way of saying. So we actually have 3 FPGAs on Cosmo. So we have the Ignition FPGA, which we have had before. We have
Lattice,
our
right?
sequencer.
S40.
Yep, that's a Lattice ICE40. We have our sequencer FPGA, so that is a Spartan 7. So we're using a Xilinx Spartan 7 for that. And then we are using up on the front for all of the hot plug IO. We're using another Lattice ICE40. And the reason that is 2 FPGAs instead of 1 is mostly just a physical choice, because you have all of these signals at the very front of the board that are all going to all the SEM slots, and there's a whole, it's a lot of pins. We got like 10 pins per SEM slot and 10, so you have 100 pins basically right there for hot plug, and the fan in to try to drive all of that back to an FPGA in the back of the board and do other things is just not worth it. So, and the ICE40s are pretty cheap. So we have that thing. I've got that mostly built out, and we're using like 40% of the logic in an 8K device. So it's not a very big design, but it's certainly nice, because then we just have a couple of lines going back and forth.
So that was a big change. We had moving to, and I mean, a lot of other stuff, it should be said, architecturally on Gimlet, we were actually really happy with. We were happy with our SP. We've got the same SP. The H753 was what we had used on Gimlet. We're using that on Cosmo. We're the root of trust, I would say. I mean, we are the company that has, I think, 2 different vulnerabilities found on the LPC55. People are very reasonable to ask us, why are you still with this chip? It's like, well, it's the devil we know. Right. So we definitely understand the LPC55 pretty well at this point. Secure silicon is really hard, as it turns out. We like our attestation. I mean, so there's a bunch of stuff that we actually liked.
Oh yeah, all of our management network stuff is the same.
Yes, yeah, because that once we got that working, there was not much of an incentive to change all that. But so the big change is this the use of soft logic, and so that kind of, and which we talked a little bit about also in the Turin episode about the fact that we're very bullish on eSPI. A little bit nervous because Turin was the first part, I believe, Nathaniel, that used eSPI, right? Because they were going to have eSPI in Genoa, and then they ripped it out, which is always like, like, oh god.
I think Genoa technically ports eSPI, but not eSPI boot.
Right, which has you like leaving so many follow-up questions, like, oh my god, it doesn't work.
Yeah, so I mean, we had decided that we were going to go down this path where we have a SPI flash connected to the FPGA and the eSPI bus, and we expected that eSPI would be the answer, but it's kind of like, well, if it isn't, I guess we can do something a little hacky and make it look like a SPI-NOR if we have to. So
we've got like, this is not going to be company ending if eSPI boot doesn't work, but boy, we would like eSPI boot to work. So this kind of brings us to a third major difference, and whether you kind of want to call this a process difference or not, Nathaniel, in terms of we were trying to pull together a bunch of things for the first time on Gimlet, and we wanted to have a way of having kind of a halfway point on Cosmo where we could validate some of these things without having to have a full board. So I think we maybe even hinted at Grapefruit a little bit on the Turin episode, but you want to describe Grapefruit a little bit? Because I think that was that was really, really important for Cosmo and its
Yes.
bring up.
Yeah, it sure is. So Grapefruit is a little board. It's in a I don't even it's the like a open NIC form factor or something like
Yeah,
this.
what is that?
So
Yeah, it is a weird form factor. What is
like
that?
it's
Yeah.
an OCP, it's the OCP form factor, I think. And so it has an edge connector, and you can stick it into a spot that like conforms to this OCP thing. So what we did is we bought a Turin bring up system from AMD. So AMD has these development platforms. So the platform we're using is the Ruby, and the Ruby had their own little their own little board in there with kind of their own BMC and root of trust and everything. So we pulled that out and we put a Grapefruit in, and the Grapefruit was basically our SP, our ROT, us like mostly the same network configuration. So but we had RJ45s on it, so we could get to the SP over the network. And then it had the Spartan 7 FPGA on there, and we wired a bunch of stuff together to hopefully be able to eSPI boot. And when we looked at the schematics for Ruby, it was like, yes, we can clearly eSPI boot there are muxes everywhere. We can like flip all these muxes and do all the things. So we built that. I think Eric did a lot of the work on the hardware design there. And that thing has been awesome because we've been using that for months in order to risk retire some of the FPGA stuff, and it's been something I've been using every day.
Yeah, it's been really good. And this is thanks to as Lukeman dropped in the chat, this is the OCP DC SEM specification, which I think I haven't looked in the history of it, but this has got to be the Run BMC, kind of have that Run BMC lineage. But the just the idea that there should be a connector so you can have a different BMC, or in our case, service processor, that has allowed us, that brought out a lot of these connections and allowed us to build this thing. We would not have been able to build this thing had it not been for this specification. So I think we were really grateful for it. And then, yeah, so tell me about the experience with Grapefruit in terms of, because we had the objective of using Grapefruit to actually, I mean, there's certain things that you can't do with a true Turin, but there's a bunch of things that you can do. So what are the things that we were able to do with that and able to actually get working before we even finished taping out Cosmo?
Yeah, so the big things we were able to risk retire on Grapefruit. So the first part is the easy part. So I have a little tiny like QSPI driver, and then Hubris can read and write to the QSPI that's on Grapefruit. So that looks like our host flash on a Cosmo. So that was kind of the first thing that we brought up, because it's like with eSPI boot, when you want to eSPI boot, then you're going to want to like fetch data from flash. So we built a little eSPI or a little Spinor shim, and Matt wrote all of the Hubris code for that, and we spent a week or two debugging all of that so that we could read and write files into a Spinor. So we did that, and then the next piece up was this eSPI thing. And so the eSPI design in general is not overly complicated, I would say, but it there's a specification by Intel, and so I took the specification and started working on our implementation of it. And so that was a decent amount of work, especially given that we're starting from a pretty low amount of FPGA code generally that we own corporately, and so we're having to build kind of all of the infrastructure to build in a new tool. So since we were targeting Spartan 7s, we had to do some work to get our build infrastructure, which we're using Buck 2 to do our FPGA builds for this stuff. And so I had some work to get all of that working, get Vivado kind of plumbed through there. I haven't been a big Vivado user before in my past career, so I have gotten the experience of catching up on Vivado. So the Grapefruit really provided like an awesome target for all of that. We could do a lot of that early, dryland work, get a bunch of stuff going there, and then it was like, now we need to stick this thing into a Ruby and get eSPI going so I can debug my the simulator is only so good, and I'm sure I need to get things working. So we eventually reworked the Ruby enough to make eSPI boot, and we're able to do a huge amount of risk retirement on our IPCC implementation, our eSPI boot implementation, everything all on a Ruby and Grapefruit.
Yeah, that was terrific. And Matt, you mentioned that there are some things on the Hubris side, because I mean, Hubris runs. We've got an SP on Grapefruit as well, so we did bring up a Hubris obviously on Grapefruit.
Yeah, and I
And
think the interesting part about hubris on Grapefruit, which I did not write, but Cliff Biffle on our team wrote this, was that the FPGA, instead of being connected over SPI, is connected over the FMC bus, which means that it shows up in the SP's memory space, just like other peripherals. And so Nathaniel and I put a bunch of work into coordinating the outputs from the FPGA toolchain with the inputs of the hubris toolchains that we could create all of these virtual peripherals in the FPGA and then have them show up and talk to them through the same kind of accessors that we would use for peripherals that were actually built into the SP's hardware.
which is really cool.
Yeah.
That's a big change. Then that's not what we had done with the FPGA on Gimlet. That was much
Yeah,
more
I mean,
like
we had like the precursor to this. So, I mean, over in our FPGA land, we've been using system RDL to define all of our registers, and so we
right.
output
Yeah.
some we output some JSON which Hubris can consume. But because of the way we did Gimlet, Gimlet was a SPI peripheral to an SP. And so while we did generate a whole memory map for Gimlet and hand that over to Hubris, it's a little strange because you basically have one driver in Hubris kind of doing all of the things. Whereas when you're sitting on, on the FMC interface, you look much more like a first class citizen to the SP's addressing. And so you're able to let Hubris write a driver for like UARTs or a driver for SPI and a driver for eSPI, and they don't have to all like be shoehorned into kind of the same thing. And so the
Right.
nice things are they get, they look like more standard peripherals that you'd write drivers for. And then maybe the downside is that you probably want to better integrate things. And so Matt did a ton of work there to better consume that JSON, and we made a few changes on our side to generate a little more of the stuff so that he can set his MMUs up correctly, and all of that really works really awesome. So
Yeah, so we can even have different peripherals in the FPGA mapped to different tasks in the SP. So like the task that's doing the host SP communication can only talk to the UART in the FPGA
Right.
and
Yeah.
would get a memory fault if it tried to talk to a different FPGA peripheral, which is pretty nice.
That is really cool. The FMC, where does that originate from? What is the in terms of the FMC bus?
I mean I think it's just an ST name for their bus. I mean, the FMC peripheral supports a number of different external things. So you can connect it up to RAM, or you can connect it up to parallel flash, or you can connect it up to a bunch of different things. And
Got it.
so,
Okay.
I
So
am not.
this is not an FPGA.
I haven't heard.
Okay. This yeah.
Right.
Interesting.
Yeah. This is it's specifically a peripheral in the the STM32.
In the
And
STM32. Yeah. That's very cool.
yeah, it is.
I
It's
don't
neat.
think,
And like there are some like there are better peripherals out there in the world, but this one is fine, and it does exactly what we need. So there are a couple of like strange errata on it, but we're in pretty good shape there. So
and did we hit those strange errata, presumably on Grapefruit?
yeah. Oh, yeah. I mean, yeah, we had workarounds for all of those things, all implemented. I kind of forgot about that because I did that so early in Grapefruit. That was the first thing I did in Grapefruit, because if you can't get to FPGA registers, you really can't do anything else. So that was the very first peripheral I wrote for Grapefruit.
And in doing Grapefruit, did we find errors in the Cosmo? Because Cosmo had not yet taped. Did we find things that we wanted to change in Cosmo, or
Yes.
perhaps potential errors in Cosmo?
For sure. Probably the big one that stands out in my mind is that the way the FMC peripheral works is you're basically like jacked into the brainstem of the bus, and so you can issue a bus transaction out the FMC, and I can stall your bus as the FPGA for as long as I want, which
Oh
could be
goodness!
forever.
I mean,
Right?
which makes sense. Like in order to have
It
that
does
kind of
make
integration,
yes,
like you do,
yes.
it's like it's understandable, but it's also like oh goodness, oh that
Right.
can
Yeah.
lead to
You
some
almost.
serious
I mean,
pathologies.
yeah, you almost have to, because like if for example you wanted to fetch data from a peripheral that's in a different clock domain, it could take multiple clocks to get it safely
Right.
crossed across over. So you do need the ability to stall for a somewhat arbitrary amount of time. Some buses do implement, like I worked on a PowerPC Core IQ P2020 a few years ago, and that one had a timeout on the bus. So after a certain amount of time, it would give up, and like it was on the FPGA then to recover at that point. Um, But in this case, there's a wait pin, and I think the wait pin is low, and while the wait pin is low, the SP waits. And if you don't, and so there are a couple interesting things. Are like, what if the FPGA isn't there? Like you haven't configured it yet, and like that pin's not driven. So we missed a pull up on Grapefruit for the wait pin,
Interesting.
and so
Yeah.
we like Cliff found that pretty quick along the way and was able to he implemented a weak pull up on the Grapefruit, so we were able to like get away with no rework there. But in Cosmo, we put a real resistor there, so it'll be strongly pulled up when the FPGA is out to lunch.
Yeah.
So that's probably
Interesting.
the biggest one we found. I would say it turns out Aaron and I found an additional problem, but it was too late because we had already taped out Cosmo, and we didn't have enough time to get all the way to the end, which is that we needed pull-up resistors on our I2C level translators. But so that's a rework on Cosmo. So.
Yeah, that's right. But so I mean, the wait pin thing is an interesting one, because had you not found that, we would have found that in Cosmo. Cosmo would have been the first time we were putting it together. And we really can't do very much without this FPGA functional. I mean, we actually need this thing to be up and functional. So it's like we would have hit that like pretty early in bring up. We would not have been able to bring up SP5. We would not be able to power on SP5 because we would have had to it would have been a couple of days or whatever it took to debug it and work around it, what have you. And during that time, it's like everything is blocked because, I mean, you're effectively like you've slipped everything by not, and by kind of pulling this out in the Grapefruit, we're able to basically hide that latency and not allow Cosmo to move forward without it, which is great.
Right. I mean, yeah, we had solid months of FPGA work done on Grapefruit before we showed. And so, I mean, like, we'll get to more of that, but like during the Grapefruit bring up week, I mean, we got to eSPI wiggles. And so like that, and we knew they were valid eSPI wiggles, and they were like, hitting the peripheral the right way. So like that, those are things that would absolutely not have happened without Grapefruit, because I mean, it would have taken me another month just to bring all that stuff up.
Right. And it would have been again another month where everyone's like kind of like, well, we can't get to the rest of the validation, and I've got like, I'm here to do the the DIM validation, and we actually can't do that because we can't power the thing up. So it's Grapefruit was very, very important. Of course, so we couldn't test on Grapefruit too. And so what were some of the things that we are going to have to, like, some things we're going to have to test for effectively the first time on Cosmo? What were some of those things?
So we knew, I mean, I just alluded to this, but we knew the SPD proxy stuff, we did not get tested on, we did not complete our testing on Ruby. And so, I mean, Aaron and I spent more hours than we'd probably like to admit dealing with trying to get that working. And I mean, it's a real kludge because I mean, we had about 3 feet of rework wire run into that thing in order because of where the DIMMs are in the Ruby and where the Grapefruit is, and the fact that they didn't intend you to do this, and that we eventually couldn't actually control all the muxes we thought we could control. We ended up needing to add wires and like remove a mux and that kind of thing in Ruby, and so we did some rework on that. But then we're always chasing. We're trying to run something at a megahertz, and we've got 3 feet of rework wire in there, and so like signal integrity is a problem, and it's just a complicated mess there, and so we were never really able to get to ground on whether that was like working or whether that was like a function, like was the FPGA code right, or was the test fixture bad enough that it's not a valid test. And so anyway, Aaron had done a ton of work on that and then handed some of that over to me while he got to go work on different problems. And so we knew that was going to be a risk going in, I would say. Obviously sequencing we could not do. But when you look at the Turin EDS and the sequencing, it looks very similar to Milan, so we weren't too concerned about that. And then a bunch, like none of the hot plug stuff, and a bunch of the other things we're going to all have to be brought up for first.
Right. And we knew that hot plug, like with that would, if we're testing hot plug, that means we've got an SP5
Yeah.
up and working. So that's a whole bunch of stuff
Exactly.
that's already working.
Exactly.
So it's fine that stuff is further down. But like sequencing is obviously going to be, we're going to hope that we've got this thing working. So I think this is all a very good backdrop for Cosmo. So we get our first boards back. We are in our manufacturing facility with Rework Electronics in Rochester, Minnesota, and this was on the Monday, and I actually thought it was going to be like a like maybe 2 days of beeping out, and it definitely wasn't. Like you guys you're able to apply power pretty quickly. I mean, tell me about kind of the process there.
Yeah, so I think a couple of things. We learned a lot of stuff in Gimlet in terms of like we know that the T6 has a pretty low impedance on its power and ground planes, and so there were a lot of concerns that we could kind of rule out right away. We also had we had a number of people there, so I know Ian and RFK and Eric spent a lot of time beeping some of the boards out. But when you have less problems than you did on Gimlet A, there are less weirds.
Yes.
I don't know if you
Yeah.
remember, but like Gimlet A, none of the I2C addresses were strapped correctly on the entire board. So
Right.
and we were building all of the humidity validate and the humidity sensor stuff.
We hadn't built any of that stuff. We built that stuff
Right.
out of our experience with Gimlet A. It was just very crude all around.
And I think when you got the engineers there, so you have Ian and you have RFK and Eric, and like they did all of the power supplies. So like they're already like super familiar with the design. They're ready to like get in there with probes and poke everything. Within a few hours, you've kind of got like, okay, we have no shorts. Everything looks reasonable. We're ready to turn power on, and then we put like a dummy ignition in there that just turns our IBC or our 54 volt to 12 volt converter, which is kind of the main the power stem into the board. So we put a simple FPGA in there that just did that one pin. And then it's like, well, okay, our whole we call it our A2 domain, but it's basically our standby power domain with the SP up and the ROT up and everything. Like all of those rails can be checked out, and it's like everything basically came up kind of as it was designed, and we're in pretty good shape there. So it was like, well, now it's time to start flashing things. Yeah.
Yeah. So which is great. So you start flashing things. So now we want to get an actual and Matt, you'd prepared we had a Cosmo hubris image. Obviously, you not able to test that on an actual Cosmo until we have one. So, and it's really easy to fat finger addresses there. We do try to double and triple check the stuff, but it's just really easy to make mistakes there. So you kind of know what you're going to find. But Matt, we were able to get a Cosmo image on there, and
Yeah, well,
how'd it go?
when I was booking the flight, I was joking that surely they will not be to the point of needing a hubris image by like 2 p.m. on Monday afternoon when I arrive. And it was basically as soon as I arrived that they needed the hubris image ready. So it was good timing.
That's great.
And
And
the first
how'd it go?
hubris image, it kind of worked. Like it flashed, we could run humility to get all the task status. I think we might have had a couple of things crash looping just due to like bad peripheral addresses and everything.
Yeah, and you had your FPGAs configured, I think, pretty much out of the chute.
Yep. And we had
Amazing.
one issue talking to the FPGA for mysterious reasons, which we will get to.
Right.
So, and did we? So, because and I had intended to be out there on Monday. Our United Airlines had other plans for me. So United thought maybe I would prefer to take the red eye and show up on Tuesday morning. So I that's what I guess I did. But so by the time,
the very first image we flashed, we could actually not talk to the FPGA, if I remember correctly, because we actually had a pin that was not one of the sync pins between the FPGA and the SP on the FMC bus was not wired up correctly. Physically, not wired up correctly.
Yeah, so we had one. There are a number on the SP. There are a number of special purpose pins, and one of the special purpose pins for the FMC had apparently been moved from Grapefruit to in Cosmo. It's unclear exactly where that happened, but at any rate, it wasn't really actually allowed to move, and it moved to it. We could have probably survived that if it had moved to another pin on the FPGA, because we would just rebuild the FPGA with a different pin. But in this case, it had moved to the dedicated pin was now connected to like some circuitry on the board that we didn't have access to. So we did actually have to do a rework there to basically not use that pin for its intended purpose on the board, and we could live with that, and we had to jumper that pin over to a pin that was accessible to the FPGA.
So that's how gnarly was that rework? Was that?
Oh, it was no big deal. It's a little jumper between two balls underneath, or two vias underneath the SP, so it's a little, it's just a little tiny wire.
Okay, and are you able to do that with it? Do you have to deball the SP to do that, or is that
no? You can So the SP is a BGA part, and both, or at least for these two pins, all of the vias were exposed out the back, so we could just jumper via to via. And
that's easy. Okay,
we basically tell Matt, you're no longer allowed to use this other pin because we just jumper to it, and right. It's fine.
Noted.
So,
right.
Yeah.
Great. Okay, so that gets all done, I think, on Monday, because the
yes,
certainly it felt like by the time
that found our second bug, or at least that one found. So after we get that, now we're able to talk to the FPGA, but there are issues. So when the FPGA responds, you don't always get you're not like, it looks like certain bits are stuck in its data path. So like if it's supposed to read dead beef, you see like, dead 01 or whatever, and so we spent a good bit of time trying to figure that out. I mean, I put the ILA, which is like the logic analyzer you can compile into the FPGA. I put that in there. Matt and I are peeking and poking different addresses and trying to figure out like, what the heck, like, why am I seeing? And so then it's like, well, the data is coming in wrong on these bits always, right? And so it turned out that was a different Hubris peripheral was also attempting to use the same pins.
Oh, yeah. Oh boy.
And unfortunately, in the process of debugging that, because it was data pins, and the data pins on this bus are bidirectional. So the FPGA gets to drive them at certain points in time as well. We managed to blow up.
Not with the SP driving them.
Yeah, exactly.
Right. Yeah. So we managed to blow up probably the FPGA pins on that one, and so that once we figured that out, though, we were able to fix the Hubris peripheral and try it on a different board and prove that everything was working. And so then we just sent that board back for rework and had the SP and the FPGA replaced.
And in fact, we got very lucky because we tested out a different board, like a second Cosmo board with the image that would have led to these pins blowing up, but we had not done the rework to fix the FMC bus controller. So we didn't get to the point where the two things would fight. And so then Ian walks over to me and says, all right, I've done the FMC bus controller rework, and hands this board to me. And I realize, if we power up this board, it will immediately blow up these pins. So I hand the board back to Ian and say, Ian, can you please undo that rework? And I can put a safe image on here.
Right. It's like, Ian. let me understand this correctly. You want me to like literally break the thing I just fixed because the fixed thing is going to break the board?
Well, by that point, I'd gotten really good at soldering jumper wires on the back of these boards. I'd done like, 10 of them. So it really wasn't that big of a deal. It took 3 minutes instead of like 30 minutes, but it was just funny.
Yeah, that is pretty funny. And good on you to realize that, Matt, that it's like we cannot power this board has become the board of death. We must not power it on.
Well, and that's kind of one of the perils of bringup is that you always want, like, we have a whole team of people there, and you're kind of single threaded until you can start like handing additional hardware out. But there's always a risk when you haven't checked everything out that you're potentially, like, you have a bug like this that you don't know about, and so it's just a problem, and you kind of have to balance that. So you want to get enough stuff working where you're like, you feel like you're safe, but in this case, like, we kind of got lucky, because had we reworked things or discovered things in a slightly different order, or had Matt not noticed that that was true, then we had to go back through and make sure that all the boards, we had 7 or 8 boards on hand. All of those had, had the correct SP image flashed before we got the rework done. So
Yeah,
and like in this case, like we didn't even lose that board. So by the end of the week, our CM had replaced the 2 parts that were damaged, and so that board is back in rotation, no problem.
So, and Ellie is asking in the chat, like, boy, like these blown up boards, are these potential souvenirs? Like, well, actually, these boards are so valuable. We need to really, really, really try hard to rework them if they're and these were all reworkable.
Right.
Now,
I mean, you figure, our FPGA is probably $100, and the SP is probably $25 or $30, and it's probably, I don't know, maybe $200 to have have a rework technician replace them, but that's totally worth it for us on these boards, especially because we only built 12 or only built 14 or whatever. So
that said, as a reward for Oxide and Friends listeners who have managed to endure this far into it can get pretty technical. I do actually have a bunch of, Aaron, those are Rev Cs, I think, right now, right? That we Gimlet Rev Cs that are dead, that are literally marked e-waste right now in the office, and we've got like I think 10 of them and something like that. So for the first Adam, we're gonna go call in show. We're gonna go for the first end listeners. So if you leave something in the chat here, we'll get you a very dead Gimlet Rev C.
Might be some bees there too.
Might be some bees, yeah. I did go through. Definitely no A's though. We've got all the A's. The A's. The A's have got some facial scarring that we when you're looking at an A, because the A's got anyway. So these things only become souvenirs when they're obsolete, I'm afraid. But we do have some that will some Rev C Gimlets anyway. But those, and then Nathaniel, we reworked those, or I should say Benchmark reworked them. And we were, hugely grateful. My God, I just go back and think about how much rework we did, how much we taxed the Benchmark rework. Obviously, like it's a service, and they, whatever. Yeah. But I guess what I really shouldn't be thinking about is our rework bill from Gimlet Rev A. But they were great on Rev A Gimlet.
Gimlet Rev A, we didn't have that much stuff done at Benchmark because we were still so broken after the 2 weeks that we had. I think Eric and I did most of the rework on Rev A's. We might have had a few of the inductors replaced and maybe a couple of chips here and there on a few different boards. But where we really used a Benchmark
was Rev B,
capability was on Sidecar.
Sidecar, right?
Or no, wasn't it? Wasn't it side? Yeah, it was Sidecar B that had the footprint mistake on the power rails. Or was that Gimlet B? I can't even remember.
That was Gimlet B, right? That was the Rev B Gimlet had the
Gimlet B.
Yeah. So that's where and
that was a brutal
they
rework.
Earned their
so
money.
That was not an easy rework.
No, and that was nasty. And we're all sitting there waiting. Like once you discover that, you can't do anything. You can't do anything until you get those boards back. So please help. So
right. So anyway, we were very grateful for Benchmark's rework for Rev B. We needed much less of it for Cosmo, but it was great because we were. But these boards, once we got the SP and FPGA back on there, they worked. So which is great. So that was really nice to not have to lose the board. Boards are expensive. So we. And then, so we're kind of we're getting ready to begin on sometime Tuesday, an SP5 power up. I know, or actually I guess in parallel now, Eric is working with the SDLE and trying to understand what our margin looks like. And he is having some issues getting this thing to emit its telemetry that we need, the SVI3 telemetry, if I recall correctly.
Yes. Yeah.
And I think unfortunately he's unable to join us tonight, but I think that I think Renaissance was hugely helpful on this. I think that we needed a firmware update, I believe was the challenge there. But I don't know, maybe you know more details on that one. Whatever that was, that problem got resolved. So
that got resolved pretty quickly. And I mean, it was nice in the sense that I think Eric didn't start SDLE work until extremely late in the second week of Gimlet A bring up.
That's right.
Whereas
Yeah.
in this case, like, I mean, by day 2, he had a board kind of to himself, and then he could, we had to I had to give him an FPGA image that just turned all the supplies on, and then he could go do SDLE. And there's a lot of control loop tuning that has to happen there, and a bunch of other things to make sure that we're meeting the margins that we designed for. And so, and like the runs take a long time, and it's kind of like a full factorial test in some cases. And so, and you gotta swap load pods, and it's pretty intensive. So he got to kind of sit over in a corner and really work on that for most
Really
of the
work on
week.
that. And then I think needed again, we weren't having things work originally, and part of the reason that we like this Renaissance part, like a relationship with Renaissance, the FAE Renaissance, Bryan Faley's been hugely responsive and was able to get us what we needed, and I think we were, from a power perspective, we're looking good. And in particular, we had talked about the Group G, which, as Eric says, Group G is for Guzzler, is this highest consuming part, and we wanted to be able to make sure that we could support a dense Turin, and it was looking good. So great stuff.
Yeah, I think sum total from him at the end, I think we had to add 2 capacitors, which
Amazing.
is not a big deal. So he did a really awesome job getting
was-
those designs. This is all a TLVR design, which I don't know the definition of that acronym, but it's a fancy control loop kind of power design. So
yeah, Ian, sorry, you say, I don't know if you've got any additional color on that.
Oh no, I was it would have been good earlier, but I think Nathaniel covered it. That's all.
But so we're looking good there, and it's time to power up SP5. Let's give it a go. And of course,
and I feel like we have high hopes at this point, because like this has gone really well.
Why do we have high hopes? How many times, how many times do we have to have our hearts broken before I guess it's like, it's part of the human condition, is that like you get your heart broken and yet your hopes still get high again. But we did have high hopes. We absolutely had high hopes.
Yes.
Just summarize at this point where you were, because like compared to Gimlet A, like it's like Tuesday night, and in 2 days we've powered up. I mean, I don't know. We probably have 5 of the 10 boards running. All the firmware's programmed. All the FPGAs are flashing.
We've got all of A2 more or less checked out. I mean,
power tuning. He's already done the tuning for Group E, and the only reason Group G tuning is not done is because the runs take like 45 minutes each, and there's like 12 runs or something. But he's working on it. Like he's got a board since Monday. He's over there, doing the thing. And we're looking at each other going, like, this is great. Like, all we have to do is put the CPU in.
Let's go.
Because like at this point, like everything I've worked on the board is done. And so my job is just like, okay, I'll keep people fed with reworked boards. Like I'll just do reworks as they come in.
Or undo whatever rework Matt tells me I need to undo, apparently.
And so I think or undo reworks, yeah. And so like things are, and I like, we get our hearts broken, but at the same time, Nathaniel pointed out to me, like, this was months of work to get Gimlet Rev 8 at that point. And hundreds of, like, 50 reworks that he did by hand,
You're making me feel that optimism all over again. So, all right, I'm right. We're optimistic, and we powered on. And Nathaniel, what happens?
Well, so they're like, in the sequencing, there are 2 handshakes with the processor. So we release like a low level reset, and then like within so many clock cycles, basically they should respond back with like 2 pins should wiggle a different way, and that doesn't happen at all. And like this is super early. I mean, it's like the earliest signs of life that we have from the processor. And so we did kind of a bunch of looking around at things, and it's like, I mean, we bring the sequencing traces out to a header so we can look at them, and they all look correct. And it's like, well, this is so early, like maybe our clocks aren't starting. So, but like we have crystals on the board because we're following, the recommendations of AMD. And but it's really annoying to measure a crystal with this without special equipment, because you can by putting a probe on it, you can change the circuit and the crystal can stop or the crystal can start. And so anyway, the long and short of this is basically our clocks weren't actually starting. And so we needed 10 mega ohm or 2 mega ohm burden resistors across there, which we had footprints for because the AMD guidance recommends that you leave space for them in case you need them. So we did have them, and so we installed. We happened to have, I think, some 2 mega ohm and some 10 mega ohm resistors in one of the kits that we had brought with us, and so we install those, and it looks like clocks are up and running reliably.
So how did we measure that? Because I mean, as you say, like this is like the original probe effect is.
Yeah.
I mean, this is like the placement of the probe distorts the circuit.
I mean, you stick a scope probe on there, and kind of hope, really. And then on these chips, in some cases, they have outputs. So in the AMD cases, because they support 2 processor designs, you can cascade some of your clocks, and so they have clock outputs that are buffered inside. So they have an RTC clock that comes out, so that's your 32768 kilohertz clock output, and then you have I think 100 megahertz output from your 48, which your 48's another oscillator. That's kind of the core thing that we use. And so we could measure on the outputs in some cases. Like if you get up past the point where the output should be on, then you can measure the outputs. And so we weren't getting there originally, but we with a little guessing, and like you could kind of put the probe near the circuit and decide that it wasn't running, and then you could touch it and sometimes it would run. So I think like RFK definitely had one point where he's like, yeah, the clock's running, but it was running when he touched it because he was he was able to get it to start. And so anyway, we did figure that out. So we reworked the boards and convinced ourselves that the clocks are starting. The RTC clock still starts really slow, but we've kind of decided that was true on Gimlet as well. And I think it's because we're weird and we're like the only people in the world who don't have a RTC clock battery. So that oscillator is actually just slow to start, and doesn't actually meet the startup times of what you'd expect, because it powered on later in our design because we take power away every time we cycle it. So we got clocks.
Nathaniel, sorry.
Yes.
I dumb guy question here. So when you turn on the power, the clock is slow. It needs to warm up, clock, like an engine.
Yeah. So I mean, crystals are funky, right? They're there's a little thing that's actually vibrating, and so it's this funky little analog circuit. And if you're too burdened or you don't have the right load capacitance, it'll take a long time to actually reach its stable vibration, and the end result of that is you don't see your clock start. Or if we're looking at the output, we don't see, the output is typically gated, so you'll see nothing, and then you'll see the clock show up, and it just.
And so, what's a long time? Is it
hundreds of milliseconds to seconds?
Okay.
So
the way that most folks work around this is just a battery to keep it.
They have
primed.
They always have a battery.
Most servers out there don't actually turn this rail off in general. So because it's never off, then it doesn't matter that it took a really long time for it to start.
Gotcha.
But and Adam, it is amazing that this whole thing starts with a quartz crystal. And it is really, the whole thing is just very physically remarkable that you're basically whacking this thing generates electricity. And I dropped a link into a video that I thought to be really interesting about why, because it is very peculiar to silicon dioxide in its crystal that causes this. And it's really interesting. And you're also just wow, this is at the absolute, the base of this is the earliest you can be in boot, right? Is having an actual reliable quartz crystal, and then you can't measure it, which is the other thing that's kind of nuts.
Yeah, I mean, you can with special equipment, but we just didn't have that on hand.
when we were troubleshooting this, we had one or both of the crystals. It's not clear at this point. When you touch the oscilloscope probe to it, you could get them to start oscillating, and when you pull it away, it would stop. And in the process of going through this the first time, it's like, okay, well, at this point, the board has the CPU installed and it's got the heatsink on it, so you can't like flip it over on top, without it flexing a little bit. So we have it stood up on its edge, and we're in there poking it with the oscilloscope probe, trying to see if there's any sort of signal on these things. And at some point, somebody brushes their hand against the heatsink and goes, guys, it's hot. And we had apparently just by touching the probe on and off of the crystal, glitched enough clock edges on the crystal to advance whatever internal state machine is in there to start turning on more parts of the chip, and it was getting warm. And so at that point, it's like, okay, well, it's a crystal thing. We will get farther.
Yeah.
If it glitches itself, at the frequency it's supposed to run instead of us poking it. And, then things proceeded from there. So,
yeah. Well, and in some cases, like on the RTC clock, there's probably a small amount of logic in their design that runs on that. And so after you get through that sequencing, I mean, something else might be broken, but the remainder of the sequencing may still happen if your 48 started.
So we spent much of, I think, the next day getting the crystal rocking.
Yeah.
And so we get the crystal rocking, and we think that we're getting further, but we're still not.
Yeah, we definitely are further. I mean, at this point, like Ian said, now we can reliably make the processor hot. But
Right.
I'm still claiming that we're not sequencing. And so like now we've sequenced past that first handshake, and we're up at kind of the final handshake. So the way this process works is you have this early handshake, and they give you back these SLP signals, and then we turn some more rails on and do some more things, and then we tell them, hey, your power is good. So we're telling them all of the rails are up and ready to respond. And then the AMD goes out and talks to the power supplies it can control and maybe has some internal monitoring. And so then it handshakes back with a power okay. So then we know it's agreed, like power's good. And then the very final thing is it releases its reset pin. And so we have visibility to the reset pin, and it should release that. And my state machine is claiming that we are not getting through that state. So we're not seeing reset release, which if you remember from previous history, is pretty much, I mean, it's like right there where we were with Gimlet A.
Yes.
Although
Yeah,
Gimlet
it would
A,
be-
we would see it release, and then it would reset, at a frequency.
Right. So we're beginning to get ready for the kind of the long grind here, and terms like, okay, this could be a while as we. And
Right.
what did we kind of explore from there?
Well, so I mean, there were a number of things. So we're still a little concerned about clocks, because it's like, yeah, I mean, they look like they started, everything's fine. So we put some things in there. We also put, so I changed some of the FPGAs. So we have some debug headers, and so I brought some of my internal signals out to the debug headers so we could watch the sequencer run on its, like as it sequences. And like
Wait,
there again,
is now the right time to talk about super dongle, or what do we call it, mega dongle? What do we call that? Donglesaurus? I'm not sure. Do you have a name for that dongle?
oh yeah, that's
do we
the
call that thing?
Oxide programming adapter. There's an RFD on it and everything.
Do we have a more colloquial name for it? Because this
It's a programming adapter.
It's a mega dongle, is what it is. It is. It's a dongle with all the trimmings.
One of the things that we have discovered over time, and it's like we probably knew this at the beginning, but it was just one more thing to change that we weren't going to change. Especially in manufacturing, installing all of the dongles on different headers. So we have like an SP dongle and a UART dongle and a ignition dongle, and so we have all of these little programming adapters that we have to connect to discrete headers on. And so our manufacturing partner, when they manufacture a new Gimlet, they're like 5 cables they have to connect in order to program the thing, and that's fairly annoying. And so one of the things that we had also proved out on Grapefruit was this this programming adapter. So we basically just consolidated all of those into one little tiny circuit board, and then we have a higher density connector on the actual Gimlet and on the Grapefruit that and I think on Minibar as well, that use this like consolidated thing. And so you just plug this thing in. But what that allows is that allows our contract manufacturer to leave all of the like all of their stuff connected to this little board, and then this little board is just one connection to our main board. And that so we have that.
Which is
well,
very
one of
cool.
the things, yeah, it's super nice. We also do have some additional debug headers. So we have like our standard little Samtec debug headers sprinkled out on the board in a few places. And those, like I've got 16 pins of debug header connected to the Spartan 7, so I can bring 16 different signals out on 2 different voltages, which is super helpful. We've used that a ton in bringing the stuff up. Yeah, so we do all of that, and it's kind of like, yeah, well, I don't know, reset's still 0, right? And I mean, we tried a lot of things, and like we went a bunch of different ways because you know, I was making changes to the FPGA. We're trying to bring various things out, and like you start to get this sinking feeling that like you're feeling FPGA build to build variability. And that's like, as an FPGA person, that's a really bad place to be, because that means, you know, probably like an assumption you have is not valid anymore. And like that assumption, you know, the tool should be telling you these things, but like if you've done something wrong or you have improper timing constraints or that kind of thing, like those assumptions don't hold. And so it was kind of feeling like that for a while. But I'm looking at the design and I'm like unable to find anything that interesting there. None of the stuff is running super fast. I'm looking at you know, my build logs from, you know, a build that like nominally would sequence and one that wouldn't, because we did at some point get one to sequence. In fact, we got one to sequence.
Yeah. Well, that's huge.
Yes, it was huge. And so we're like, oh, look, I saw eSPI wiggles. And so then Robert and I thought we would be cute and not tell anybody. And so I built a new FPGA that had the ILA in there, so we could do more FPGA stuff, or we could look at some of that stuff, because you
the
had
ILA being the embedded logic analyzer.
The embedded, yes, yep. That I can compile that into. That's a Xilinx tool that you can compile in Vivado. And it basically just gives you a little like model sim type, you know, wave view of things, and it samples into RAM in the FPGA and spits it out over JTAG.
Which is super cool. And we had
Yes.
talked about this. I mean, this is like a great thing about soft logic, is the fact that you've got the ability to do this. And I think, you know, this is one of the things we're going to be able to leverage. I mean, there were a bunch of reasons why we're not able to use kind of open FPGAs. Right. We had to kind of use a Vivado toolchain. But it's like, hey, one of the nice things about this is we would have this particular tool. I had never seen this, but I was super curious about it.
Yeah, and you had missed so I had already pulled this tool out to help debug our FMC problem. But you, due to your United delays and other fun, had not managed to see that. So you had only heard the story. So you wanted to see it. So I was like, hey, this is great. We're going to bring Bryan over here. We're going to show him the ILA and the little thing. And then rapidly through the course of our conversation, you're going to figure out that we're actually booting, right? And so like this was like my, you know, cute idea.
I gotta say, like, this is like cracking the seal on something pretty dangerous. You know, this is like you are introducing like pranking in the bring up lab. I mean, I just think you gotta handle this carefully. Is this true? Is this pranking, or is this like kind of Oxide demo bit? I mean, no, I agree with you.
We learned
showmanship from, yes.
Yeah, we learned from, you know, local horse not to prank you at bring up. But
yes, fair.
So at any rate, so I get a new FPGA loaded in there. We call you over. Ha ha ha. We're gonna be super cool. And then we get a
suspect a thing, by the way. As it turns out, like I am an absolute mark. If you like, oh hey, I want to show you an embedded logic of the FPGA, I will willingly, like, I'm just like fish chomps down on the bait. I'm just like, I've got no clue that there's.
We owed it to you, right? We were gonna show it to you, so it was gonna be kind of a cute way to show it, and then also, like, you know, get the cheers of, hey, we're booting. Except that when I built that FPGA, it didn't boot. And
Well, and so like you're showing this to me, and
yeah,
you
nothing
two
happened.
are like obviously very disappointed, and I'm like, what? Okay, this seems like I don't know. Yeah, this is interesting.
Right. Yeah, and I mean,
And they're like,
yeah,
It's weirder.
it was doubly sad because because nothing happened, but you didn't think anything could happen because we're still having we're still having problems sequencing. You're kind of like, well, what did you expect? You goofy people. So, and we're
yeah,
like,
right.
well, actually we did boot once, or we started to boot, and something happened. So
I'm like, you
yeah,
guys, you had an SP5 over here booting, and you're like, it was just your first thought was like, let's go. Anyway,
well,
I was,
so
I was impressed. I was impressed.
yeah, I
I
mean,
was impressed
part
with
of
that
it
kind of
too was
emotional
like
regulation, frankly.
it had started booting and then it stopped, and we didn't know why, and so we were going to
Right.
need the ILA anyway, but it was just so. At any rate, so it doesn't boot, and so now we're into this world where like I have an image that I have made that seems to like somewhat reliably sequence,
Well, no,
but
because you're like,
anytime,
it did, dude. You explained to me like what happened. I'm like, yeah, I swear, but so then we put the old image back on,
yep,
and that image, sure enough, like does get to eSPI
sequence,
wiggles.
yes,
Yeah, and you're like, oh
and
no,
it's like,
what's going on?
like yeah, I know, because like I mean, these are problems that like you should be avoiding by design in general when you're doing FPGAs, and I've been doing FPGAs quite a while, and like so it's never a good feeling because now you're into like, is my tool chain lying to me? Did I miss some kind of clock crossing somewhere in the design? But like again, all of this stuff is like all of the sequencing is all in single domain, and it's like 125 megahertz, and it's not very complicated, and like I've got all the pins coming out, and I can see that like I continue to do the I wiggle the right way and everything. So um, so then we're like, okay, I don't, so I'm like, going through build logs, all the stuff, like really can't figure it out. We get another build, we put more things on the debug header. We get a build now where like when I attach, I have a Salier connected to the debug header, we seem to sequence, and when I pull the debug header away, we don't sequence anymore.
Wasn't it the opposite?
Or maybe we put it on. Yeah, I mean
Because
it's like
we wanted to get like the Salier on there to understand, like, okay, if we
yes,
can just understand, like, we need to look at these eSPI wiggles and understand exactly where we are, so we can
right,
understand like why we're not making further progress. Like, oh, we get the Salier, and they're like, well, now I don't boot at all. Now I don't do anything.
right.
You're
And
like,
and it's right, and
good
it's complicated because
computer.
every time we send something out to the debug headers, we're getting a different FPGA build. But
Yeah.
it's like kind of weird because like I can go back and rebuild those builds, and I can rebuild those builds with like other minor changes and not make any change. So it's not total build to build variation, but like there's something strange going on here. And then we're like, well, maybe there's a floating pin somewhere else. And so, loading the bit stream, or like, I mean, anyway, we went, like it's like the stages of grief, you go to bargaining and, all the other things. So,
Okay, so put this sadness in the oven here,
yes,
because we do actually have we've got a kind of another opportunity to validate things without the SP5 working. So, because Ian, you'd been working with Matt and Aaron on getting Minibar fully functional for, and we talked about Minibar a couple episodes ago, but getting Minibar fully functional for Cosmo, which is going to be very exciting.
Yeah, so one of the things that was happening in parallel with trying to get SP5 to boot was, because it's Tuesday, and right about this time, Benchmark releases all of the rest of the Minibar boards to Doug and I. Doug has the big mechanical chassis there for the first time, all assembled, which is really cool. He's got one of the Minibar Lite units there, and so I do some quick checks. There was one more rework we had to do on them, just pulling a bunch of ESD diodes off. It had been installed backwards, and then they were ready. And so Matt and Aaron and Laura jumped on them, got all the software loaded, and I don't know how long it took. To me, it was like half an hour because I was working under the microscope, but it seemed like pretty much immediately they popped up and they're like, we're done, it works. And so we sort of look at each other and go, well, let's go get one of the flight test gimlets, from the production floor. Let's put a sled in it and see what happens. And so they go get a sled and shove it in Minibar, and some LEDs come on, and Aaron goes, "Oh, yeah, we can see, we can see both the ignition links." And someone, Matt grabs his laptop, or Aaron grabs his laptop and plugs it into the Ethernet port on the back, and go, "Oh, I can talk to the SP. The management network's working." And so we sort of look at each other and go, "Well, we could get a Cosmo and put it in there." And so the Gimlet comes out, and one of the Cosmo boards that doesn't have a CPU in it, but it has everything else on it, goes in there, and LEDs come on, and plugs the laptop in, and yep, management network's working. And so we were able to really quickly check out, something that we wouldn't have been able to get to until we had a rack, to and a dedicated to that purpose. So it was really cool.
Yeah, and while Nathaniel is kind of weeping over on the SP5, the Minibar is having wild success over here. It was Nathaniel. Sorry to be hopefully you felt we were, but it was actually great to have, and I just dropped a picture of kind of Team Minibar in there as we got that was great to have, because Matt, we were able to really validate the entire management network on Cosmo, and Aaron, because I think you plugged in your laptop, was pretty great.
Yeah, it basically went from Aaron's laptop to the RJ45 jack on the back of Minibar to a PHY to the management network switch into the Gimlet over the backplane connector that normally goes into the rack backplane, and then through another PHY and then out to the SP. So yeah, basically the full chain.
For Cosmo as well, which is great. That was. And Aaron, what was the work that was involved for that to get to in order to get that kind of all the way over the line?
Honestly, not all that much. I feel like we had two snafus. One was I had an RTL bug with the button that tripped me up for far too long. The power button that actually controlled power to and from the sled, and I feel like we had I'll just go look at the commit history to figure out. There was like one other thing that we fixed. I think Matt, the SPI interface, maybe didn't work immediately out of the box, but for the most part, the goal with Minibar was to just reuse as much software as possible. So it was just kind of like sticking down blocks. I think Matt, you maybe had the VSC parts configured in a new to us way.
Yeah,
but
the
otherwise, a
PHY
lot
was
of it
actually the PHY was running in SGMII to like RJ45 normal Ethernet mode, but luckily that is like the most common use that 99% of people are using for these PHYs, so it's a lot less weird to bring them up like this.
And so that was great to have just all of that. I mean, it was just very validating. I mean, like literally and emotionally to have, and Ian must have felt great for you to see kind of Minibar in its intended purpose. And of course, Doug had this just absolutely beautiful enclosure for the thing. I mean, it's amazing. So that was, but Nathaniel, meanwhile, back now to take your sadness out of the oven. We are actually like it felt to me like we were, because you get to the point where you are seeing true eSPI wiggles in the logic analyzer, which it definitely felt like at that point I felt like a very important, like we know this thing can work. There is something that is preventing it from working reliably, but this thing actually can work.
Right. Yeah, and it's weird because like we would see eSPI wiggles start, and then like I've looked at a lot of eSPI traces with all of the work on Ruby. One of the neat things we did with Ruby is we broke all of that, all of those traces out to headers so I could like see the SPI. So I've been looking at eSPI traces for the last 2 months or more, and so I know what they're supposed to look like. And like I see valid transactions. I see exactly the start of what's supposed to happen, and then things just stop. And so it's not like my logic. It doesn't look like I'm sending anything wrong. It doesn't look like the SP is asking for anything, or the SP5 is asking for anything wrong. It just stops, and so that's weird. And like we spent a lot of time building a lot of FPGAs and like that's kind of where we ended bringup for in terms of Cosmo, because it was like, well, this can work. We have something we have to go figure out. And so Eric and I are going to take sleds home with us, and we're going to hold the rest of them there and let them start getting all of the rework that we've identified. Which isn't much. I mean, we maybe have 9 or 10 little reworks that need to happen, and then we'll try to figure out this, identify any other further rework, and then get these sleds distributed out to the team.
And then the fact that it can work, I mean, how did you? What was your anxiety level kind of coming out of that first week? Because I mean, obviously there is an issue here. I just feel like this may take a little while, but I felt like, unlike with Gimlet, where we definitely didn't know it can work.
Yeah.
In fact, it didn't work, and it's similar with the T6 when we had all the frustrations with the T6, as Aaron was saying earlier in the chat. Like, why won't you come out of reset? The Oxide story.
Right.
It just feels like I mean, so it felt like there is something amiss. Clearly, something is floating somewhere.
Yeah.
But what was your kind of level of anxiety coming out of it? I mean, it just feels like, we just need a couple of like good nights of sleep and, a little bit of a restart. And it feels like it's not going to take too long to nail this.
Yeah, I wasn't too worried about it. And I mean, there are answers to all of these things, and we will find them. And while it was a great 5 days out there, it's 5 pretty long days, and you're kind of on the whole time, and so it's helpful to just set things down. We had to take the afternoon to pack the car up basically, and we bring most of our lab equipment out there, Eric and I do. So there's a good bit of stuff that loads back into the van as we get ready to head home. And it's like, we'll get these boxed up, take them home, take the weekend to recover, and then on Monday we'll hit it hard again and find some answers. So
okay, so what happens on Monday?
So on Monday, it's interesting because I'm like, man, I really want to get working on this, but also my entire lab is in boxes, and I've got to put enough stuff back together so that I can solder if I need to, or I need to get a scope out or my DMM. So I took kind of the morning to unpack enough stuff to where I was like, okay, I feel like I can sort of work again. I still had some stuff, I still had about half the lab packed up, but it's like I'll source that stuff if I need it later. And so I get to building, and I go back, and it's like, okay, there are a few different things. Like, it could be environmental. So does it even, if I take this image that seemingly does boot, or seemingly starts trying to boot, does that still happen at my house? And it does. So it's that's good.
Okay. That's good.
And,
yeah.
And if I take a nominally broken image, then it is also broken. And so it's like, okay, that's good. And so we're kind of I just want to rebaseline everything, relook at everything. And so I spent, probably most of the afternoon messing around with that. And man, it's been such a wild week now. I'm trying to even remember. I think I did discover the issue by that evening, or was it Tuesday morning?
Oh, you definitely discovered it that evening. Yeah. Sorry if you don't remember where you were when you discovered the issue, because I definitely remember where I was when I saw you drop in the chat.
Yeah. So, it's one of those things where you're like, okay, I just need to go back and look at absolutely everything again. So, I'm not going to look at clocking anymore. We're pretty sure that that's fine. This is feeling like it's an FPGA problem. What in the world could I be doing wrong in the FPGA? And so, I go back looking through, and at a certain, I discovered that the reset pin that I'm looking at is supposed to be an input to me, and I have it configured as an output. So that is not great. And but I'm and it's a little there's some VHDL inside baseball and stuff here, but it's a so it's an output, but it needs to be tri-stated because so it's an input, so it doesn't really matter. I had it as an output that would be tri-stated because in general, all of the things going to and from the SP, we try to tri-state so we don't cross-drive our buffers and that kind of thing. So I had made this a tri-state output. And so after I found that, I'm like, okay, like that's a problem. I definitely need to look at that as an input, but given that, I don't understand how we sequence,
Right.
because
How do we sequence? How
like
does this ever work at all?
how could we
Yeah.
ever sequence? Because I
Right.
don't understand. And so, and I'm like, one of the things I had noticed during the week was like there seemed to be sensitivity to what I put on my debug pins. And I was a little bit lazy, and I made my debug pins in outs, and made some assumptions about how like how the synthesizer and the tool should behave. And it's unclear to me if my assumptions were incorrect or if the tool has a bug. I still haven't gotten to ground on that yet, but the long and short of it is I have an undriven, so like deep inside my design, this pin is an input, but up at the very top level, I made it an output. So what you effectively have is a signal in your design that has no defined driver. And so when the
Right.
synthesizer runs, you will get a warning for this, but like if you've ever looked at FPGA tools, there are lots and lots and lots of warnings. And anyway, so this reset line has no driver inside the design. Up at the top, it's an output. Usually what I would expect the synthesizer to do at this point is it will pick a value for you, and it'll throw a warning that says, I picked a value for you. That value is typically 0 in most of the stuff. Like most synthesizers will just pick a 0 for you, and they'll drive a
Right.
0 out for you. And
It will drive
it's
something.
like, yeah, and like that 0, and like the way I had my design done, that 0 inside the design should drive a 0 out, and effectively
Yeah.
I would have held the processor in reset.
Right. Right.
And
it would have been
that's
clear.
all.
It would have never worked at
Yes,
all, and it would have
it
been
never would, and
presumably
we would have
clear.
gotten here.
Yeah.
We would have gotten here much faster, I think.
Right.
And like that's kind of a normal thing. The in a 2P system, so if you have two processors, this line typically gets shared between the two, so that the system comes out of reset when they're both happy. And so like it's totally fine for the SP will happily look at the signal, and or the SP5 will happily look at the signal and just not continue in its process until its friend is happy. But its friend was
Right.
the FPGA. So the interesting thing is. Because of what I did with the debug connector, and because of how Vivado like connected all of this stuff, it basically took the input buffer from my debug pin and drove that net inside my design that was not driven otherwise. So it basically wired an input, and that's surprising to me. I mean, I spent
like enemy action. I mean,
yes. So I fixed this first, and immediately everything like sequence. I mean, like boom, we're good. And so I'm like, okay, this is great. But now I need to understand how in the world did this ever work? Because and so one of the things these tools do is they'll give you a little schematic that kind of shows you how your logic is. So you can see that in the bug that's linked there. In Quartz, there's issue number 333. And Vivado shows you what it did, and it did exactly what I just described. It connected the input buffer of my debug pin to this internal net that had no driver in my design. So we did have a floating pin. That floating pin, though, was my debug pin, and when we would touch it or do other things, we would occasionally allow my my signal to tri-state. And when my signal tri-stated, the processor, which was out of reset, then would continue out of reset like it should. And I did stick that code. So I made a simple reproducer. There's a reproducer in that bug now, and we'll see what Vivado has to say about that. I did run that in Quartus, so the Intel tools, and I got the circuit that I would have expected there.
Which is driven 0. Yeah.
Which is driven 0. So I would expect the internal logic to have picked that, and we would just drive all the things 0. That makes sense to me. I can make Vivado do that if I give my internal signal a default value, and that's what I sort of would have expected here. So we have, I have a request out just to like figure out if that's spec behavior. I did kind of go into the language spec a little bit, but I'm decidedly not a language spec expert, and trying to like get to ground truth on that is more time than I had this week to continue looking at that. So,
But this is also one of those, because I mean, and the thing that is so interesting about soft logic is it has these properties of both hardware and software. I mean, truly, right? I mean, this is it, and the issue you had has this kind of software pathology of like, I change seemingly something innocuous and I get is
yes.
reproducibly now correct or reproducibly incorrect, which definitely
Yep.
feels like and you know, Adam, I mean, I think it's I'm certainly in our group had many times where you're like, I know there's going to be a single bug that explains all of this behavior, but God damn it, if I've got no idea what that could possibly be. And this feels like certainly an FPGA variant of this, because ultimately, Nathaniel, this explained everything. It was just like, yes, I guess if like if the devil is in here actually hooking my debug header up to my reset pin, I guess it all does make sense. Remarkable.
Yeah, and it's certainly an area as an FPGA designer that makes us uncomfortable as well, because like there is a lot of magic going on here, you know, behind under the hood. And so we have all these rules that we follow, and we you know, we put timing rules in and that kind of thing. And to make sure that like the variability that is inherent in this process doesn't end up being a functional change for you. And so then when you think you have followed all the rules and you still see build to build variability, like, you know, that's like, you know, you hear the Jaws theme song and you know that like probably you've done something wrong. But it makes us pretty uncomfortable.
Well, I think also one of the challenges I just got from you when you were just talking about kind of like that part of the challenge with this tooling is that you also get a lot of warnings that you need to ignore that are
an immense amount,
which makes it then really tough when it's like, oh, I'm supposed to know this because there's like one load bearing warning in this sea of warnings that I need to ignore in order to, I mean, it's like, boy, that's really tough.
And interestingly, because of the way this worked, my runs that work and my runs that don't work often have the same set of warnings, but it's just like the warning apparently means that they made this circuit, and this circuit was not what I intended. So
right. Yeah, God, absolutely brutal. Well, so this I mean, ultimately, I mean, when you went back to kind of like first principles, and you were able, I mean, you got this thing like nailed pretty quickly, and now we're really at this point, and this is last Monday, this is a week ago. Things really begin to cook at this point, and we start getting because I think you've got Unix up like within a day or two, right? Yeah.
I mean, not even, I mean, it was, I feel like it was almost hours, because like once this works, then I mean everybody else had all their, you know, we had RAM disks and we had, you know, all the things. So I mean by Tuesday morning, I think we were, or Tuesday sometime we were booting. So
I do like the fact, Nathaniel, that my first reaction to this, I mean, aside from like the verbal exclamation of this when you nailed this issue, was I did say that I appreciated you considering our need to provide podcast content in the
right.
I mean, it's great content, I gotta say. That we have a but it was and so then we hit the SPD issue. You kind of made a passing mention to that you that was took you and Aaron maybe a day or two to get that resolved, and we turns out we needed what, stronger pull-ups.
Yeah, so we use these. So the SPD I3C bus runs at like 1.1 volts or something, and so we have to level translate out of the FPGA for that, because the FPGA only goes down to 1.8. And so we use these level translators, which we had put on Grapefruit, but again, by the time we got to doing SPD stuff on Grapefruit, Cosmo had already taped. So Aaron had done a ton of work there. I mean, like you might want to talk through some of the, like, you know, terrible VNC shenanigans into my basement. But he had done a bunch of stuff there, but we just couldn't convince ourselves that everything was like totally working. And so I don't know, Aaron, you want to fill in any details there?
Yeah, I mean, we'd been booting off of Grapefruit. Yeah, and I was using, I'm like tunneling into your house SSHing through machines to use a oscillator that's hooked up to like I don't know, a couple bucks. It's really painful, but
Yeah.
it's better than
Yeah.
driving to
So
his basement.
yeah, I have what we call a butler in the basement. So that's an Illumos box that has the like humidity tool chain on there. But we're not running Cellier on Illumos, and so I have another Linux machine.
I mean, we're barely running it on Linux.
Yeah, running Cellier, and so then with a little bit of like SSH port forwarding shenanigans, Aaron could reverse tunnel a VNC connection from my Linux box out over the VPN over to his house, and get a very slow graphical display.
Yeah. So that was rough.
Yeah, Aaron, that was enough to nail it.
Well, it was that was how we were doing some of the initial development, and like, I mean, the weeks that I was working on this in my spare time was like, I felt like I was just chasing ghosts because of the voltage translation problems and the fact that I think we had touched on this in the beginning where we can't we're not allowed to know how to change the muxes on the Ruby, so we have to like hack in these like this SPD signals because we're basically putting ourselves in between the processor and the DIMMs, which resulted in, due to all the mechanical form factor stuff, our multiple feet of wire that we're running the I3C bus at. And so with like there were just so many levels of jankiness that it was tough to like have high confidence in some of the weirdness we were seeing, and it got to the point where we're just like, well, we'll try it on Cosmo, and we'll just make it so we don't try to play any tricks. We just let the CPU talk to the DIMMs, and we get out of the way. And that was working just fine on Ruby and Grapefruit, so we expected it to be the same on Cosmo, and it wasn't. And yeah, we spent some time. I mean, we were looking at ILA traces. We were looking at the Cellier again and probing and just seeing strange things with it would work. It smacked of Quartz 333. Where
yeah, interesting.
you could drop out the RSPD proxy logic and watch the CPU talk just fine to pins that were effectively tri-stated. But as soon as we wanted to try to get in the mix a little bit, things would kind of like maybe wiggle once and then get stuck. And yeah, I mean the problem ended up being after Nathaniel, I think you had looked at. Were you probing power supplies and like we were making sure that everything was connected, because we saw like one across both buses. We saw like one of the SDA lines was just hanging low, basically, when we'd have our image installed.
Yeah. So on Cosmo, like the end result was basically that once an I2C line went low, it never came high again. Except sometimes it did. And so the level translators that we're using, they say they have 10K pulls on them, but if you read their data sheet, they talk about those 10K pulls really being high keepers, which means that like I2C is complicated, or I3C is especially complicated because you could active drive high, active drive low, or you could run in I2C mode. And the level translators kind of suggest that like their 10Ks are there for high keepers. So once you've driven it high, they'll keep the bus high, but maybe don't function totally as actual like solid pulls.
Yeah,
well, I mean the funny / sad thing, about all this is that before we ever went out to bring up, we expected we were going to need to do this, and then we spent another day looking at this, from end to end, and then arrived at the thing we already were suspicious of that we would need to go do.
Right.
And because of the the jankiness of our Ruby Grapefruit hack, we were doing some of the some things like, okay, enable the internal pull-ups on the FPGA, and actually let's active drive this bus because we're driving 3 feet of wire, and part of our application is us trying to also use the bus at a higher speed. So getting some of those things out of the equation led us to actually look at the physicality of what was going on. because it didn't seem to be working as it should have.
Yeah, so I mean, I did a bunch of builds. Aaron and I chatted some on Tuesday, and finally I was like, okay, I think I'm just gonna break out and put the 2K pulls down on all this stuff, and let's just see if that moves the needle, because this is sure looking like a floating bus that isn't really doing the right thing. And so the way we have this, we've got 2 buses from AMD coming to the FPGA, and so that's a level translator for each of those, and then we have 2 buses going from the FPGA out to the DIMMs, so that's 2 more level translators. So you end up having 4 level translators, and you have ins and outs on each one. So that gets you 8 pulls per level translator, and we have 4 level translators. So anyway, there's a bunch, or maybe 4 pulls per level. 4 pulls per level translator and 4 level translators. So we have 16. 16 little resistors. So I was able to tack 16 little 2K resistors down on the back
I was
side of
going to
the
ask,
board.
so it
Pretty
was
easy.
2K. Yeah. Okay. Yeah. Interesting.
Yeah, so I picked like 2.21K. That's a 1%, pretty standard resistor when you want a nice strong pull. And this stuff is all at 1.1 volts, or it's 1.1 on one side and 1.8 on the other side. So that seemed like a reasonable choice, and we want this to run pretty fast. And on the FPGA, if we want it to go even faster, we can active drive it if we need to. And then sure enough, of course, I put this in, and then boom, booted. So that was Tuesday afternoon, I think.
Which was, that was great. I mean, now I'm not just that, and in particular with DIMMs training, like we're actually like, because I mean, you need to have the SPD working so the thing can see the DIMMs, but now it actually has to like train the DIMMs. And this is now, we are around the dark side of the moon. Although thanks to the FPGA, we actually have got, we get little morsels of what it's up to. On Gimlet, it's like it is in the dark side of the moon for 1 minute and 12 seconds. Not that anyone has ever sat there with a stopwatch and counted that over and over and over and over and over again. The training time is actually longer, and we're going to be doing some things we talked about some of the things that we're going to do to actually kind of cache that information, but we actually got a little bit more information so we can see what this thing is actually doing and what bank it's training and so on. So but it is able to make it all the way up, which is great. We've got a computer. Now and it actually, I was surprised. I don't know. I'm not sure. And no, Dan and Luke, but I'm not sure to what degree you all were around. But I was surprised how far we made it on that boot. It was great. We basically got all the way up to multi-user. We got CPUs up. We got a lot of things now working, which is great. I think we were now just shy of Nathaniel just getting hot plug working, right? That was kind of the last major thing we needed to get working.
Right. So none of the PCIe stuff came up in an expected way. And so then it's like, well, guess who's back in the hot seat? Oh, that's me, because we took all
logic, they said.
Yes, we took all of the all of those level translators and everything, and put them out, and made basically the FPGA is emulating all of that. And so it's like, okay, I've got good simulation coverage for all of that, but like this is the first time I've even seen traffic coming out of the chip. And so it turns out that the only bugs that I actually had there were around my my indication of stuff like to the like how I had wired up things to the hot plug controller. And I think I also was not necessarily, when they would read an input pin, I wouldn't necessarily show the outputs. So there was one minor little thing there, but all of the rest of it was just like I had improperly translated stuff from the sum slots and that kind of thing, to the correct pins on these level translators. But all the I2C stuff, like I pretty quickly got a trace there, and it was like, hey, this all looks like really normal. We're acking and doing all the things like we should. So
that is awesome. So I mean, to be expected that we're going to have, there's going to be, because these were another things that we couldn't actually test with Ruby, right? And Grapefruit, like we actually needed actual real Cosmo. So, but then the fact that like we now have, you were able to get all that stuff resolved and we've got actual devices. We actually by the end of last week, you are actually seeing NVMe drives. We are seeing which means we've got PCI training. You've got, and so at this point, like we've got certainly way more computer than we had when we recorded our Gimlet episode years ago. But we've got a lot of computer at this point. We've got still things to do, plenty of work to go do. We've got to go do dim margining. We've got to go look at what that eye diagram looks like. We got to go look at PCI link training. How's that looking? How's that looking for the links that we know are going to be a little more marginal in our simulations? But damn, we're looking good. It feels good anyway.
Bryan, about how long did this level of bring up take with Gimlet?
I mean, I like 5 to 6 months,
Man,
honestly. Right?
incredible.
Yeah,
Maybe
well, like,
slightly
okay,
less
what I
than
was
that.
out there, I was out there in February, I think, for T6 still wasn't up, and like we have
T6
T6
was not
up
up.
in manufacturing mode, so hopefully tomorrow we'll get T6 flashed and it'll be up in its like Gen 3x16 mode. And I think once we do that, we'll be ready to like get the remainder of the boards, through rework and shipped out to our coworkers.
Yeah, it was a long time because everything took longer, and we this was the 499 ohm resistor on T6, and we had the clock issue. I mean, we had just a bunch of issues that were and fortunately, we learned a lot from that. We got much better experience. In terms of like we got experience with these specific parts, and now we know we know that needs to be a 499 ohm resistor for the T6. We know how to do the I think the resistors to select the internal clock. I think we are very very familiar with that one on the T6. But then also we just again, Grapefruit was absolutely clutch. And it's been really good. We've just been and again, further things to go, but now things are it feels like, Nathaniel, also things are really parallelized, and we've been able to just knock tons of things down. We had an issue where it would only work with the unsecured parts. And Lukeman just today nailed that issue, and we're and sorry, Lukeman, if I'm speaking too soon. I know we got, but that was looking promising anyway. So we're making to answer your question, Adam, we are way further along, which is great.
It's awesome.
It's been it's been fun, Nathaniel. I think this has been. I mean, I think it was I think we obviously wanted to get further in that first week, but I would say, given where we are now, I don't think we would have thought we'd be. I think this is exactly where we want to be. I would say. So
yeah, and this
really
feels more like how a complicated board bring up should go. So
yes,
the appropriate amount of pre-work and the fact that we're building on stuff. I mean, like lots of hubris exists already, and we have all of these great tools now that we didn't have day one. So it's super nice we can rapidly figure out what's wrong and close on the stuff.
So it's good stuff. So we got work to do to get this thing out in a product, but we are excited to get it all the way over the line and do all the next things we need to go do to get this. But we're gonna live. We have a computer. It's gonna work. Thank God. Which didn't. There were moments where might not have felt that way. Not that long ago. So. Well, Nathaniel, terrific work, and obviously a bunch of folks, and I know Eric couldn't join us, but the fact that power was so clean on this, as you said, two caps, and it's been.
And there's just been an immense amount of teamwork. I was telling some of the electrical guys earlier this week, just every time I have to go to the schematic to look, the schematic even just feels so much better than Gimlet's did, where Gimlet had a lot of hands in there and a lot of iterations on it, and our new schematic just is so readable, and all of the guys have done a really and really I spent very little work on this project in schematic, so that's a credit to the rest of the team. They've really made a really nice artifact that's fun to use. And like, I dread having to go back and look at Gimlet when I was trying to compare, like what's different between Cosmo and Gimlet. And the Gimlet is just so nice to read. So like Ian and RFK and Eric especially and Tom did a great job there.
Well, and I'm hoping everyone's going to be able to appreciate their craftsmanship, because I want to get that schematic out there. So I want to.
Yep.
I want everyone to be able to look at the glory that is, because it is great, and like just the way it was done, the notes on it are great. If you're writing, it's the way a schematic should look. It's really terrific work. So, well, and thank you for coming here and regaling us. I thought it was definitely fitting that we had an issue that is in the netherworld of like, it really feels like it would be nice to get more help from the FPGA tools. So, I think that fitting for us that we had such a bizarre issue that was at the root of it all, and kudos to you and everyone for getting that resolved so quickly and onward. Great stuff. All right. Thanks, everybody. Now I got to get Morris Chang at this point, Adam. So now the pressure is very clearly mounting. It's like, okay, great. You pulled Cosmo bringup out of a hat. Like, what's next? You got to get Morris Chang. So I think we've got no choice.
Looking forward to it.
Exactly. All right. Thanks, everyone.